When discussing Jupiter, it's impossible to overlook its iconic Great Red Spot. This massive storm, the largest and most violent in our solar system, has fascinated astronomers ever since Robert Hooke first observed it in 1664. Over the years, various space missions have studied this colossal phenomenon. Probes like Voyager 1, Voyager 2, and the Cassini spacecraft collected valuable data during their flybys, while the Hubble Space Telescope has continuously monitored it from Earth. Hubble's observations revealed that the storm is shrinking. Once large enough to fit 3 Earth-sized planets, it now accommodates just over 1, with its current diameter measuring more than 10,000 miles, a significant decrease from its former size of 25,500 miles. Additionally, the storm's wind speeds increased by 8% between 2008 and 2020, and its shape has shifted from oval to circular. However, the storm's depth remains a mystery, as observing Jupiter in detail from Earth poses significant challenges. To better understand it, close-up and continuous observations are essential. NASA's Juno spacecraft, launched in 2011, has been conducting such observations since its arrival at Jupiter, providing crucial insights into this awe-inspiring storm. In 2016, the Juno spacecraft began orbiting Jupiter, studying its magnetosphere, cloud tops, radiation belts, and the composition of its moons. These observations have provided valuable insights into the mysteries of the Great Red Spot. Despite these advances, many questions about the storm remain unanswered. Recently, astronomers using the James Webb Space Telescope discovered a previously unseen structure in the atmosphere above the Great Red Spot, along with an unusual glow of light hovering over this massive storm. The exact cause of this glow, and the strange atmospheric pattern is still unknown. Initially, scientists speculated that sunlight might be responsible, similar to how sunlight creates auroras near Jupiter's poles. However, researchers now suspect a different mechanism may be at play. You are watching University of Universe. Henrik Mellin of the University of Leicester, the study's lead author, remarked, "We thought this region, perhaps naively, would be really boring, but it is, in fact, just as interesting as the Northern Lights, if not more so. Jupiter never fails to surprise." In this discussion, we'll explore the enduring mysteries of the Great Red Spot. How has this colossal storm lasted for centuries? What powers it, keeping it active for hundreds of years? Why has it recently started shrinking at an accelerated rate? And most intriguingly, what is the strange structure above the storm? The Great Red Spot's longevity is linked to several unique characteristics of Jupiter. As a gas giant, Jupiter lacks a solid surface, allowing the storm to move freely within its dense, swirling atmosphere. Additionally, Jupiter's rapid rotation, completing one rotation every 10 hours, creates powerful jet streams that help sustain the storm's spin. The storm itself is an anticyclone, rotating counterclockwise roughly once every 6 days, with wind speeds reaching up to 580 miles per hour. On Earth, anticyclones form when high atmospheric pressure forces air downward from higher altitudes. The mechanics behind the Great Red Spot's formation, however, remain a topic of ongoing research, as scientists work to unravel the secrets of this extraordinary feature. Anticyclones are typically associated with clear, warm, and dry weather, while cyclones form around low-pressure centers, causing air to rise and resulting in cloudy, windy, and rainy conditions. While the formation of anticyclones on Earth is well understood, the origins of Jupiter's Great Red Spot remain a mystery. Scientists are unsure exactly how or when it formed, or why it has persisted for so long. One hypothesis suggests that the Great Red Spot is trapped between two opposing jet streams, which act like conveyor belts, maintaining its spin. Another theory points to the vertical flow of heat and cold within the storm, which could help sustain it. A crucial factor in its longevity is Jupiter's lack of a solid surface, meaning there is no friction to slow the storm's rotation. In the mid-1990s, NASA's Galileo probe detected lightning and massive thunderstorms near the Great Red Spot's boundary. Scientists theorize that these smaller storms might feed energy into the red spot, sustaining it. Since the red spot is a shallow system, disconnected from the planet's core, smaller thunderstorms may transport heat from Jupiter's interior into the atmosphere, fueling the larger storm. Through fluid dynamics, smaller storms rotating in the same direction can merge with the red spot, boosting its energy. However, storms spinning in the opposite direction may create drag, potentially weakening it. Interestingly, the Great Red Spot has been shrinking. Some scientists speculate this could be due to fewer smaller storms feeding into it, reducing its energy supply. Alternatively, an influx of slow-moving or oppositely spinning storms may be colliding with it, causing drag and depleting its strength. Adding to the intrigue, recent observations by the James Webb Space Telescope revealed a previously unseen structure above the Great Red Spot. This discovery highlights the continuing mystery of this iconic storm, as scientists strive to understand its dynamics and evolution. Jupiter is one of the brightest objects in the night sky, easily visible on clear evenings. However, apart from its striking auroras, the rest of Jupiter's atmosphere emits only a faint glow. This faintness makes it challenging for ground-based telescopes to capture detailed images, as Earth's atmosphere can blur the view. The James Webb Space Telescope, with its advanced capabilities, has been able to overcome these limitations and recently focused on Jupiter's Great Red Spot. This observation uncovered several complex structures, including dark arcs and bright spots, within the storm. These peculiar patterns, along with the bright glow above the Great Red Spot, have left scientists puzzled. A new theory suggests that these features might be influenced by atmospheric gravity waves within Jupiter's atmosphere. Gravity waves, unlike gravitational waves that are ripples in spacetime predicted by Einstein's theory of general relativity, propagate through a planet's atmosphere. Similar to how ocean waves crashing on a beach create ripples in the sand, these atmospheric waves are generated deep within Jupiter's turbulent lower atmosphere and travel upward. As they rise, they alter the structure and emissions of the upper atmosphere, potentially explaining the observed anomalies around the Great Red Spot. While incident sunlight accounts for much of the faint light seen from Jupiter's atmosphere, researchers believe another mechanism, likely linked to gravity waves, is shaping these changes in the upper Jovian atmosphere. On Earth, gravity waves occur as well, but they are far less intense than those observed on Jupiter. The team now plans to conduct follow-up observations with the James Webb Telescope to study these newly detected features and wave patterns in greater detail. These future investigations could reveal how gravity waves move through Jupiter's upper atmosphere and how they contribute to the intricate structures surrounding the Great Red Spot. Thank you for watching, and stay tuned for more updates on this fascinating celestial phenomenon.